Good evening or good morning. Today, we are glad to have Dr. Luo to present this topic, like unlocking super separation within the hardware. So it's mainly focused on the our DLC column, which recently introduced by Welch. So let's welcome Dr. Luo.
All right. Thank you, Jack. So welcome to my webinar. So it's wonderful to connect with you guys from all over the world. Yes, I hope to this section to be as interactive as possible. So your insights and questions are invaluable as we shape our approach together. So thank you again for your dedication and hard work. Let's get it started. So as Jack said, today we're going to focus on the Inert hardware. Come on, oh, it is here. Okay. So basically, this consists of three sections. So first one is first section. We're going to talk about why, what reason we need to use Inert hardware. So basically, talking about the corrosions and adsorption happens in a stainless steel hardware, and then try to explain the mechanism. Then later on, we try to talk about as we know, for those the stainless steel on the surface, you see oxidized layers. So I'm going to explain the impacts of this impacts of on the separation by the oxide or metal oxides. So we can briefly talk about a little bit about the stainless steel alternatives. After that, I'll give you a picture for what we've been doing here, and then offer you some tips for operating this LC system. So this question being asked by many people. So basically, if you look into the world in chromatographic area, there are two groups. Some people, basically mostly from bioseparation, they believe that stainless steel hardware is not good for the separation, such as the proteins, DNA, all these kind of biomolecules. The separation being impacted by the hardware. But another group, like smaller molecule, people always say, I don't care about that. But let's see what's happening. So, in many times, so people try to say, okay, when they do the quantitative study, so the expectation is get the linear relationship between among those the mass and the signal. However, many times you get the curved like this. So in other case, you'll see the poor performance, like tanning, like broadened peaks. So all those contributed many times by the hardware. So this is not new. Actually, if you dig into the history, you're going to see that many times. Before we talk about that, so I'd like to show you guys briefly about the stainless steel in the system, in a typical LC system. So in this diagram, you'll see the many components linked by those blue lines. The blue lines are stainless steel capillaries. And then from the pump head all the way to the detectors. But for this, the components, even from the in the mobile phase reservoir, you'll see that there's a filter. That's a stainless steel. But if you check the pump head, so I think most of you have seen this, right? So a lot of stainless steel components. The next will be the mixer. The mixer to mix the mobile phase A and mobile phase B, but it's made of the stainless steel. And then come to the injector. So injector, of course, the stainless steel again. And then come to the column, the blue one. So without a stainless steel, we don't have a LC system. But what we found, and what people already found, is the impact from stainless steel. Here use the bio separation gain. So typically, because in the system, we have the capillary, the stainless steel tubings. So how does tubing behave during the separation? So this is a paper published in 1983. It's a very old paper. It's 40 years ago. But the picture shows here on the most left side. So this is the capillary. It's weird, and in order to the inner surface. So inner surface on the most left side is pretty flat. But the middle picture, you'll see that. So this is after this tubing exposed to buffer, and the buffer dried in the tubing, and then they grilled the tube in order to see the inner surface. You'll see the not a pitch. And on the right side is the same type of tubing, but this time the buffer and the proteins flushed in through the capillary. Here you see the picture, you get a white stuff on the surface. So clearly, the stainless steel can absorb the proteins, the samples. So there's an impact, even you from those capillary stuff. The next is the stainless steel components in our system. Here's the one example here. You see in this system, there's the pump, right? So the flow rate is 1.5 mil per minute. And the mobile phase goes through the system first, go through the filter, and then go through the regulator, and then there's a controller. So before this regulator, the pressure was set at 60 psi. After that, the pressure set at to 800 by using the flow controller, yes. So after flash this mobile phase through this whole system, you see the pressure gradually increase until it go up to the maximum of the pressure that pump can handle. So in this, the big picture on the right side, so you see that this is the configuration of the controller. And before this is applied to the flashing the mobile phase through the regulator, the inside is pretty shiny. But now it's something built up after the pump appeared. So this is the whole set for the experiment. So the paper was published in 1985. But guess what? What kind of a mobile phase being used here? It's organic. It's acetyl nitride and a methanol. So without seeing this paper, even I cannot imagine. And pure acetyl nitride, pure methanol, stainless steel surface can be oxidized. The corrosion can happen. So of course, in this set of the experiment, there's different kind of surface being used. From left side, the table, from 1 to 3, there's stainless steel tube wasn't treated very well. But number 4, the tube was passivated by nitric acid. So this is the typical way in nowadays LC system, the system being, all this stainless steel being treated by this way. People believe that by using nitric acid to treat the surface, you'll get a very dense metal oxide that can protect the surface, can make the surface inert, can make you safe. But actually, it is not. So people say, oh, there's many types of stainless steel being used in the system. Are they doing the same thing? Yes, exactly. You see that the corrosion happens continuously in most environments, including low pH, of course, and even the hydrochloric acid. These people, we can imagine, everyone can agree, yes, hydrochloric acid is not good. But what about DMSO? What about phenol? What about citrate? Fluoride, EDTA? All these kind of things can impact the surface. And another study says, oh, even if you run the system faster, you'll get the corrosion happens faster. Here's the example here. So it says using the 316 stainless steel, the flow rate is 1 ml per minute, but the ID is very small. So of course, this is pretty fast flow. But you see another thing I need to point out is the mobile phase. This is the sodium chloride. That's something very dangerous to your system. By this way, it says 0.1 microgram per millimeter square per day. That sounds like not much, but if you calculate for a month, for a year, that's a significant amount. So another thing for the corrosion happen in the component is in the injector, because in the injector there's a certain switch, right? So for this kind of switch, that cause the corrosion happens fast. So that's why your injector can fail very often. Another thing is interesting, but I don't think this happens often, because it says like if you have two non-harmful solvent, like halide impurities in hydrocarbon, if you use the non, it's okay. If you use methanol, seems okay. But if you mix these two, the corrosion happens right away. So last component elemental is the metal itself, like iron. Everyone knows iron is not stable in air. But what people do, so they use nitric acid to treat the surface, as I mentioned in the previous slides. Since stainless steel is not that stable, so what's going on here? So actually, it's a we can say it's an electrochemistry way. So here I use a galvanic cell system here. So in this diagram, it shows the equilibrium between iron, the bottom brown area, and then iron oxide, but it's kind of a purple, dark purple on the right side. And then the light brown color, that's the ion in the solution. All these three systems forms equilibration. But when the oxygen presents, the ion atoms being oxidized. So this is the way like passivation pass. You get a stable metal oxide on the metal surface. But there's another reversed way. You see here. So there's metal oxide, the ion oxides being dissolved back into the solution. So that's the corrosion happens. So we say on the surface we have the metal oxides. it's not steady state. This metal oxide, actually, it can be dissolved, like what we see here. So if you have one atom moved out, released to the mobile phase, and then oxygen goes down and it another atom. So if you look at the whole picture, so basically the oxide layer going down, but on the top being dissolved. But this is the ideal situation. So if something happened, like here is a gap, the oxide layer cannot go down anymore. It just stay there. I mean, the bottom one stayed there, but the top is going down. So eventually, you get a very thin oxide, metal oxide on the top, but you also got something stick out, make the column surface not flash, not smooth anymore. So this would definitely impact the separation. So let's look at the chemistry, chemical properties of metal oxide. So it's being reported in this paper. This was published in, come on, I cannot see that, this, I'm sorry, I cannot see that, what behind the level there. Give me 1 sec, I can figure out that. Oh, that was in 1962, actually pretty old paper. Oh, thanks. All right, so since there's a PI for this oxide compounds, so when the pH is less than the PI 7, so the surface becomes positive. So what's going to happen? This is positive. It will absorb the acids. So another way, when the pH is higher than 7, you got a negative surface. So negative surface can absorb base. And something else also can impact the separation. So if you have the impurities like those 4 ions in the system, in the hardware, it will be released to the mobile phase and then grabbed by stationary phase, and then becomes ion pairing. So any metal sensitive samples will be stick to the surface and get you into the trouble. All right. Now before previous slides, we talked about the say the capillary the LC system. Basically, we focus on the LC system. So now let's look into the column. So here's the setup. So for this one, it was published in 1987. And here basically compare, let's just focus on the column and the system, compare these 2 components. So which one contributed more to the corrosion? So the setup here, A is the empty column tube with the fret. The B path is the just PTFE tube. So by looking at the B, so, anything contributed to the let's say the ion concentration is only contributed by the system, not by the column anymore. So by comparing A and B, we get a sense. So how is which one contribute more? So you see in the table in the A, you see that the ion, the magnesium, nickel, all these concentration very high. But if you look at B, it's barely there. This was published in 1987, so it's like near 40 years. And in that time, so the system is different from nowadays, but even at that time, you say the pump and injector didn't net to the detectable level. And it's believed there's like a 96% contribution is from the fret. But recently, our colleagues in Waters, they published another paper. They studied this LC system and columns in Waters. So there is two systems here. One is UPLC. The second is arc HPLC. Arc HPLC is they claim this is the one can resist. It's the inert system. So it's been promoted for years. Anyway, today let's look into the surface area here. So it says fret area is for the fret area is like this is absolute data, the 2.1 by ID 2.1. And for the column area, it includes the fret area. And the LC system, the surface area is like that. So I did some calculation here. So if you compare the LC system to the column, it only occupies less than 30%. But for the second one, less than 15%. But of course, absolute data is high. And if we compare the fret in the column set, so this time the fret is not as high as we just saw in the previous slide. That's 96%, but here it's only 35% or 26%. In previous slide, people use 50 and 4.6 ID by 50 millimeter. But I use this data to make the same calculation here. The fret occupy like 47%. It's not like 96% in previous. But nevertheless, the column set contributes the most surface area. So that means, so any corrosion happens in the system, column hardware will contribute the most. So how high can this kind of corrosion can impact the separations? Here's oh, okay, that's fine. On the left side, you see this is the compound they call neutralistic compound on the most left side one. And this is a higher, beautiful peak. But on the right side, there's two split peaks. People never understood at the very beginning. But then figured out this is the same compound, but being a naturalization happened to these these compounds, give you two different configuration. So how can that happen? That because in this system, and ammonium and acetonitrile and pH 10 to generate NOx. And NOx react with amine, give you the naturalization reaction product. And the experiment designed by the people in this group, Dr. Mayers. So they published in 2013. So they found that first of all, they need to remove the chromium oxide from the surface, and later on, oxidation of ammonium by ion catalyze. So it believed without a catalyzation, so this reaction is very hard to happen. And this was demonstrated by the nitrogen was demonstrated from the ammonium. This was demonstrated by the isomer 15 nitrogen. And then there was a study that you have to use the acetonitrile if you use the methanol. the story is completely different. So this is one example for the hardware can change the separation or even give you a lot of deep science knowledge. The next is about epimemization. So you see just one compound inject onto the surface, and then on the left side. So on the top one is the S epimer, but it gives you 4 peaks. But then people say, oh, can I understand that? So they try again, use R isomer, that's the bottom one, but still 4 peaks. The difference is the ratio between R and S are different. So what's going on here? So eventually they figured out, oh, this is because this compound, you see that sulfur, this kind of a group, it can be inhibited by certain path, give you compound 4. And then further give you compound 7. And how can that happen? Because we have the metal ions in the mobile phase. This metal ion and the Gemini cyclical hydroxy group. And then this compound, they form a complex. This complex, either if they don't do the elimination of the group, they go back to make the R and S changes. This group of a compound, this group take this group away from this compound, they will give you number 4. Anyways, so this also is the contribution from the hardware. So seeing hardware is very popular. Not popular, but very often to be seen is the signal is pretty weak. Like this compound, it has one phosphate group, and it's pretty weak signal here. But if you use Inert hardware, you see pretty sharp peak. Then people say, oh, can we use a different material to replace stainless steel? Yes, you can. So first example is like use titanium. But by using titanium freight, you do see the significant lower metal extracted from the stainless steel from the system. Another observation is by using titanium, the lifetime of the C18 column increased 8 times. That's incredible. However, this metal is expensive, is brittle. Also, it is incompatible with several conditions, say acids or base. So it has limits. So another material can be PIC. Yes, it's this kind of very wonderful material too. Yes, it's inexpensive, it's flexible, it's no absorption loss. Sounds great. But limitation is this kind of material cannot handle high pressure. So you cannot use this for UPLC at all. And another problem is the variance of this production of this kind of material varies. So that gives you another, say, like a extra column volume. You cannot predict, cannot calculate well. The third one is this material is incompatible with THF, DMSO, methylene chloride, and base and acids. So third one people being chosen is oh, we can use alloys. So you say like MP35N That's a wonderful material. Yes, it is wonderful. It can resist the corrosion. However, it is expensive. It's difficult to machine. And it's very hard to make the surface flat or smooth. So, and it's incompatible with several conditions, say the pH, extreme pH condition. The last one is HST, called hybrid surface technology. And this is being introduced in most recent years. And Waters being promoted this kind of quantum hardware a lot. It seems like it solves a lot of problems, but like some people did weird experiment. What they do is like they put this kind of column and pH 10 at 90 degrees for 57 days. This crazy experiment. However, after that experiment, the surface changed. So this has a limit. So just to let you know. All right. So after that, I'm going to give you what we do here. So we call this is a diamond-like carbon. So why do we use this? Let's back to, I'll just give you briefly introduction about this technology. So this is a very popular area in 1980s, 1990s. At that time, people believe this kind of material can be used to create a super semiconductor, but very, very quickly, people realized it's impossible. So in this picture, basically show you there's two different ways to create diamond-like carbon coating. So on the top, it's a high frequency CVD. On the bottom is a high temperature. So by doing this way, either way, the same. The diamond gradually deposited onto the surface. And then people can use this to coat the surface, to do the milling, drilling, cutting, tracing, grounding. All this is like a mechanical stuff. But people did find some unique applications. They coat this to like biomaterials. The biomaterials using this kind of coating can extend the life cycle of material and promote cell growth. That's really good. So by looking at this, so we think, why do we apply this technology to our column? Let's come to this. So you see the column picture shown here. It looks like a ribbon, right? Different colors. Anyway, so we have the coating method is a high frequency power source. We use that to deposit the introduce the carbon atoms in the hydrocarbon and then producing a stable diamond coating with sp3 bondings on the column surface. So what are you seeing here is the surface like that. It's pretty, this is a 40 micrometer, and then it's a dense coating. And then by using a XPS, you'll see that the carbon is just one peak. It's an sp3 hybridization. The advantage by using this is make the surface inert and overcome the adverse effect of the column wall on separation. The next is make the diamond coating offers higher hardness and tensile stress. So one worry comes out from that. So since we introduce the carbon to the surface, can that increase? We increase the hydrophobicity. That's something everyone will worry about. The same thing here. So we did one experiment here. We did compare the comparison between with or without coating. So because for samples, typically people use this to QC the C18 columns. So you see that the red that represents stainless steel hardware, the green represents the DLC hardware. The whole peaks overlap each other very well. That means we don't need to worry about much. We don't need to worry about at all, actually, about the surface change. So then we use this type of column to do the separate, to apply this column for different separation. First, we use this for proteins. So here, just use a cyclone C. So as you know, cyclone C can be easy oxidized, becomes a peak like the red one. This is happening in the stainless steel. So the peak should be at the green position. That's in the DLC system. So definitely using a DLC column hardware, we get a better protein profile. That's for ion change. The next will be for SEC, size exclusion. So I'm sorry, the green line is not very clean here, but you can see some trace here anyway. And the red one is the stainless steel. It's short, flat, but DLC give you sharp, narrow peaks. Next will be the another. This is an antibody. So again, the green one shows the higher intensities compared to the stainless steel. This one is works on the sample on the right side. You see that the structure. It has one phosphorus group in this small compound. On the top row, this is data from the stainless steel column hardware. So all this experiment was done using the LC mass. Compare the signal we obtained from stainless steel hardware and DLC column hardware. DLC column hardware offers almost 10 times higher intensity compared to stainless steel. Here's for about those for the nucleotides. So on the most left side, you see that's for adenosine monophosphorate. So that's just one phosphorate group. The green one represents the DLC column. The red one represents the stainless steel. So it's clear that using the DLC system, the adsorption being significantly reduced. The same thing for this, that with a two phosphorate groups and 3 phosphorate groups. And the last one is just for adenosine itself. But even this, you'll see the better signal, the higher intensity of using a DLC hardware. Next, about vitamins. So for the vitamins, in this case, it's just an acid. In the acid, yes, just one acid group. But even one acid group, what do you see? There's a little bit improved signal of DLC hardware. And then this is a vitamin B2. You see the improved one again. Vitamin B6 improved. Vitamin B7, the signal being improved. Vitamin B9 also being improved. So clearly, yes, if you use the normal column hardware, that's a stainless steel hardware, you still can do the job. But if you want to detect the trace amount, it's better to use DLC column hardware. This is compare the acids. So this is monic acid. So without DLC, you will see the short, big tanning, but with the DLC, you should see the very sharp peak. Of course, there's a still tanning, that's a different story. And this is the citric acids. Without the DLC, probably we cannot tell that's a peak. This one is just a mixture. So you use the taurine and mix with ammonium, ethylene, sulfonamide. You can argue it's not that significant, but at least the peak gets sharper. That's pretty much I have. So for the other experiments, we're still developing more application and more testing on our hardware. So we're gonna update you after we get everything done. So next section is we'll be talking about some tips we learned from what I already show you here today. First, for columns, yes. So we know that column hardware contributes most of the corrosion problems to the separation. So for those samples sensitive to matter, it's better to use inert one. So like use DLC.
I think we lost your voice.
You lost my voice?
We cannot hear you.
Really?
Hello?
Wait, hello? Hey. Hello?
But we can hear you here. It's normal.
Who's saying can you hear me?
Yeah, yes.
Okay, we're gonna continue. All right, so first is the column, because we have been demonstrated the column is the most component contributed to the corrosion. So when you working with those samples sensitive to metal or metal oxide, better to use inert column hardware. You can use of course DLC, but if you cannot get DLC image, you can try PIC. But there's no titanium column hardware because that's very brittle. You cannot make the column. Anyway, so then for the system, so here's my my 2 cents. So first one is use a degasser, because we from that mechanism, you see that the oxygen is crucial in the corrosion process. So if you can reduce the oxygen concentration in the mobile phase, that will protect your system better. The second is, so whenever you use the water or neutrals, you use the like buffer, salt, acidic or base situation, mobile phase, better to flush your system regularly. The next one, try to do the maintenance, like check valves, check seals, tubings. And then sometimes we do the works by ourselves. We always proud ourselves we can do everything. But remember, if you use the stainless steel tube, you cut it, the better to do the preservation. Otherwise, you introduce the corrosion into the system. All right, but the last one is follow the manufacturers or troubleshooting special needs recommendations, right? Next one is the mobile phase. So try to avoid high chloride content or other highlights. But sometimes, like for protein separation, people like to use sodium chloride. Be careful, all right? So minimize water usage. Try to maintain the pH, or try to avoid strong acid, but sometimes you have to use it, flash the system right away. And if you have the sample you have to handle with your system, maybe you can add another bit of EGTA to your system too. In that case, the ions can be surprised by the EDTA, and then everything will be good. But remember, EDTA is not things that can grab the ions, that will break the push the equilibrium to the ions release to the mobile phase that make the metal oxide being dissolved faster. Remember that. So whenever you use EGTA, be careful. The next to avoid leaving a corrosive mobile phase in the system. And the last one is if you do the extended storage, use a proper storage solvent, like mixed water or organic solvents, right? Yeah, the worst scenario, say you don't have an inert column, you don't have an inert system, what can you do? Well, here's the example, just increase amount, see that? So on the top is the stainless steel, the bottom row is the peak, right? But for the stainless steel, even for this one, if you increase the concentration to 250, you still get a peak. Not bad, but you just need enough amount of the sample. But next is, if in this case, whatever you try, you cannot get the peak. So then you have to either find an inert column or just stop the project. That's very bad. Next, the summary. So today I'll try to share with you what I learned. What happened to the ALC system and what happened to the metal oxides near and what is the mechanism. And there's some alternatives. Yes, you can try that, but be aware of all those limits. And another message to take away is that you can the majority contributor is the column hardware. So in that case, so when you work with the sample like a nucleotides with the acids and with those some very complex sample, it has amine, has the acids, or have some other groups, so it's better to choose the inert system. And yeah, of course, we are here to offer the DLC columns hardware for you. Let me know if you need any help. Before I finish, I would show my appreciation to my teams. So here's all people contributed to this webinar. They did a lot of work. Without their contribution, I cannot talk today. Next, thank you. And I have time for questions.
Thank you very much for Dr. Luo's webinar, and I think this is a very informative webinar, and I see a lot of old friends here, as well as some people from Welch India team. So just in case you have some questions, then we will have like 20 to 30 minutes for the Q&A session. If you have any questions, you can go your left side toolbar. There will be a Q&A section, and you can type your question there, or just raise your hand. I can unmute your microphone.
Any questions? Oh, that's two. Is it possible to use DLC columns for ion chromatography? I believe so. Thanks, it's a good info. Can we give DLC packing hardware in what is cell or estimate HPLC column range? Yes. Is this product in development stage or is it already already introduced? And I would say we almost finished development, but it may take a little bit more time to introduce to the market. The recording available to us? This is the question to check. Is the webinar recorded available to us?
Yes. This webinar is fully recorded, and just in case you need to record the whole information, then just contact us. We will send you the recording.
Next question is, what about the frets in the DLC column? Are the frets also coded? Yes. Can DLC columns also improve columns knife? Well, this is a new product. We are working on that. We will tell you a story maybe after a year or two, because this is a new, so we cannot say how much knife time can be improved. But definitely, from my personal understanding, you should improve the column knife because it stops the corrosion on the surface. And you can imagine that this is a diamond coated. So diamond, you know diamond, how hard the diamond is, right? What is the most popular application that use DLC column? So I would say, as I show here today, I would say like nucleotides and vitamins and acids. So there might be there's some more application, like people may work on the DNA. So this should be good too. And even like for proteins, we do see improved signal and a better picture, right? How does the DLC affect the where is it? Oh, here it is. How does the DLC affect the columns lifetime and durable compared to traditional columns? Yeah, this is the question I think I just answered, because the hardware is new, so we just started. We are doing this right now, but that would take, I would say, it will take a year or two. We can tell that story. Can you please share if any applications for amino acids, peptides, nitrosamines? Yeah, we work on those kind of samples. We will update you later on. Thank you. What are the next ones? What are the different phases available for DLC columns? So basically, we can note any columns, because this is, you can imagine this is just the column hardware. So no matter what type of phase you need it, we can note it. Do you have DLC columns in UPLC range? Yes, we do. What is the chemical composition in MP35N and hist? I guess the hist, you are talking about a HST, right? That's water stuff, right? And MP35N, I think that's the iodide, consists of what is that? Chromium, nickel, and 7 different kind of metal. The HST is they call hybrid surface technology. So they didn't disclose the information about that. Basically, people always guess that is the same like water's BH particle, right? As we know, some column manufacturers are using PIC material to avoid corrosion. Yes. Is there any specific advantage of DLC according to? Oh, of course. Compare DLC to PIC. First, as I point out, the PIC cannot handle like acids, cannot handle base. Because my experience was when I use PIC capillary running pH 10, so it can last like 20 hours. Later on, there's some tiny hole somewhere. The mobile phase start to spread anywhere. So I just cannot find where it is, but I do observe the pressure dropped. And also for the PIC, it cannot handle higher pressure. Say for UPLC, you cannot use PIC. But the DLC, of course, you can use for you can use for UPLC. You can use for those harsh conditions. So let me know if I answered your question or not. If not, just let me know. I can make it clear, right? Can we do DLC columns in progressive purification columns as well? So what size are you talking about? If you're talking about a 10 by 25, this kind of stuff, or by like a 21 by 25, I mean, listen, the ID, you're talking about a 10 millimeter or 21.2 millimeter or 30 millimeter, of course we can offer that. But remember this it's a coating. So we need the price will be higher compared to the normal column hardware. It is more suitable for LC-MS application or HPLC copper. I would say for both. There's a talk asking for. It's more suitable for LC system application or HPLC application. I would say it depends on the sample, right? So for like a nucleotides, the hardware is sensitive to both. So like for AMP, you don't see the signal. And neither LC mass or UV, right? Or normal HPLC. So DLC can be used for both. In which application it is here more or showing difference between regular response? Those the examples I showed today, as I just mentioned. We for those nucleotide samples, for those like vitamins, acids, basically you see the difference. What is the main benefit of DLC column as compared to SS column? That's because DLC columns offer the inert surface. This inert surface prevent corrosion and prevent the adsorption and prevent the metal catalyzation. Will DLC affect the chiral separation? That's a good question, but I don't. Well, working on the this kind of application, but I don't see why this will affect the chiral separation. It should be the. I would say it might be better because in one example used, as I showed in my talk, like there's a naturalization happened, right? So that makes the R and S that becomes one S sample getting in, you get a CR. One R sample getting in, you see S. But using DLC, you won't see that. When can we have sample columns for customer testing? When do you need? So let me know. Is any other quantum brands that have this kind of DLC? No, we are the only one in the world. Well, this technology is very new. If I talk about, yes, apply the DLC to chromatography, yes, this is new, but this technology exists, yes. Any other questions? I think I reached the bottom now. Oh, I think got one more, right? Since it is a carbon-based coating, weight affect retention times. Oh, yeah, that's a good question. But that's why in my talk, I try to show you one example. The one example I showed is just compare the typical QC method for C18. The C18, the theory there is, let's say if the DLC increase the hydrophobicity, that will be all the compounds with hydrophobic naphthalene, like toluene, like this kind of compound. If DLC increase the hydrophobicity, the retention time of this kind of compound should be increased. But actually, we didn't see that. So based on that, I would say no, it's not affected. Is DLC quantum more helpful in LC mass analysis for synthetic organic compound rather than biomolecules? I would say for both. For bioseparation, you definitely see like that it did stop the adsorption process of protein to the surface. But for the small molecules, yes, because for organic synthesis, normally you get a very complex sample. But DLC will help you to stop any interaction come from the hardware. Do you have DLC guard column on hardware? No, we are not working on that yet. So why do you ask that? Maybe we should consider that. This is the first time I got a question like that. Thank you. Any restricted sorbent or salts? Nope. But even I say no, we're still doing the test right now. So we try to see if we can destroy the surface by using very harsh condition. I'll keep you guys posted in the future, right? Is there any pH restriction to this hardware? We haven't seen that yet. So we try to test in the strong acid and strong base. So we try to figure out in the near future. As I told you, this hardware is it's developed recently, so we need time to come up with the whole solutions or whole sets of answers. DLC will be made in standard profile or tube. And what? No, in the comments. Will be made in standard profile. Oh, so question is, DLC will be made in standard profile or tube profile. No end connection. I'm sorry, I need to be confused here. Are you talking about the column hardware is like referring to the standard one, like a normal stainless steel, or there's some special design? We basically we use like a normal column set and then coat the surface, right? So there's no special design over there. Let me know if I answered the question or not. Thank you. Oh, there's some more. Means the inert and ionic connections of the column will also be. Oh yes. So basically, whole sets. You see the column tube, you see the frets, you see the cap, and everything coated, except the station face, of course. Do you have the DLC application references in your website? Where can we find the application? That's a good question. We need to get this updated as soon as possible. Now, currently, we don't have that yet, but we're gonna update quick soon.
Okay, I think that's the end of the webinar. So thank you for attending this informative webinar. So hope we can see you again in the next webinar. I hope so, very soon. So see you next time. Thank you again.
Bye-bye.
Have a great day. Bye-bye.
Great day.
Bye-bye. Bye-bye. Thank you, Dr. Luo.
You're welcome.